This, and the other learning resources in this course have been made possible by funding from the European Commission's Erasmus Plus program.
So for today, session 5, let's look at the presentation. There are some slides in this presentation that, that also cover the same topics that we already discussed last Saturday. So I might skip some of the slides, but the focus here is, okay, we know how to acquire our pictures. We know the difficulties that can occur, the challenges that can occur during the acquisition of these pictures. We know how Agisoft will match the different photos together. It will look for characteristic points and it will match all these characteristic points to make matching points. It will use these matching points to make a triangulation of your images, of your cameras, resulting in a sparse point cloud as well. And then using these oriented photos, it will make a dense point cloud, which actually corresponds with the geometry of your feature of interest. And then you can make a triangular mesh and you can make a textured 3D model. And that's where we stopped last Saturday. So what I would like to do today is go in a little bit more detail about the use of ground control points, because the problem that we have so far, or that we have experienced so far, is that if you have your 3D model, you make a picture, you make another picture, another picture, another picture, etc., 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 is that actually all the measurements that are taking place on this 3D model, they are related to the pixels of your photo. So they are all in pixel coordinates. Maybe, but I'm not quite sure, there is a metrical system in your 3D model based on the focal length of your photos. But even then, you can imagine that if you're working with a reference distance related to your focal length, so let's say that's 25 millimeters or 8 millimeters or 50 millimeters or even 100 millimeters. If you use that reference distance to model a statue or a facade or something else, in that case, the errors, of course, will definitely diverge, and the geometric quality is very limited. Not the internal quality, but the absolute quality. So the quality that you will have if you do measurements on your 3D model. So what we actually have to do here in this case is assign absolute coordinates. So X, Y, Z coordinates that you measure with a total station, with a GPS, or maybe even with a simple ruler. We will assign these coordinates or these reference distances to our pictures, to our pixel coordinates. And by doing that, we can actually perform the exterior orientation, the absolute exterior orientation, which is actually the conversion of pixel coordinates to real world coordinates. We have two options to do that. In one way, we can use targets, so black and white targets. If you follow the presentations of next week about laser scanning, we will definitely use these targets because the center of these targets are quite easy to measure using a total station or GPS. So if you have a flat surface like a terrain, you can position these ground control points, these black and white targets, and use your rod to measure the center of these black and white targets, or you can aim at them using your total station. And by doing that and making a photo, it's very easy to make the correlation or the relation between your ground control points, the physical ground control points, the real world coordinates of these points, and the pixel coordinates of these points in different photos. We will start in a more difficult fashion, being natural points. So the exercise that we will do is actually covering a facade somewhere in Ghent. And on this facade, I have selected 9 ground control points that are more or less easy to trace using difference in texture. So we will see how that works. They're actually natural points that you can use. So for example, if I disable my my background, let me see if that's easy to do. No. Video, choose vertical. Voila. If I choose my if I disable my background, and you would use this photo for natural points, then for example, if you can see it here, this point here, very sharp object can be a very good natural ground control point, or here the end of this green object can be a very nice nice natural point. both with targets and with natural ground control points, it is very important to respect the distribution of your points, both in X, Y, and in Z. So in all the three directions of your Cartesian system, the distribution of your ground control points should be as equal as possible. And by doing that, you will actually spread out the possible error for the translation, rotation, and the scaling of your 3D model. So in this case here, it says optional, but it's definitely not optional in this case. This is a typo. We will work on a facade in Ghent. So if you go to the data repository, so I go to geo.hogen.be/heritage. By the way, if you leave this SC out and you go to geo.hogen.be/heritage, you will find one of the first websites that I built, just explaining the summer school with some data that we acquired in the previous years. So, for example, if you go here to the laser scanning point cloud, so you can just click on it, and then here you have a point point-based representation of the laser scan data. Very limited point cloud. It's only 1% of the entire point cloud, but this is actually the city center, the Venetian city center of Navprio that we're looking at. And this is point cloud based, and we will discuss how to make this in next week. This is one of the models that was actually the topic of our session from the day before yesterday. And for the last session of this specialist course, you will see how to make something similar like this. We have a panoramic image with some clickable content on it. We can go from one picture to another picture, and I'm really looking forward to show you how to make something like this and how to incorporate this in your own project. But that was not what I was going to show you. Today we will work on session 5, the session 5 data. So if you click on demo data, I would invite you to do so. If you click on demo data, you will end up here, get these data. So you will get a series of images, 9 images starting with DGI underscore and then a certain number. You will see a file that is called GCP, which is actually the topographically measured, or the a priori topographically measured ground control files, and you will find an overview of the location of these different ground control points. Accompanied with that, I will give you here in the presentation some meta information, some metadata about the images themselves. So they are acquired with a DJI 4, if I'm not mistaken. I think it was the DJI 4 Pro with a CMOS sensor. Here you see the physical dimensions of the sensor dimensions expressed in pixels, the physical pixel size, the focal length. So the focal length, the physical focal length, and the 35mm equivalent. So after applying the crop factor, so the difference in diagonal, the index of the diagonal, you can find the crop of the 35mm equivalent, and the number of pictures. It's not 15, but it's it is 15 pictures. Yeah, 15 pictures. Voila. Also in that file, as I already said, you will find a text file that you can just open in Notepad or even in Excel or any other text editor program. Ground control file, ASCII based, with a header. So you will find a hashtag ID, which is the name of the point, an X, a Y, and a Z. I don't know why there's still an X here. It's probably an error from my side. And then under it, you will find a column with the ID of the ground control points, the X coordinate of the ground control points, the Y coordinate of the ground control points, and the Z coordinate of the ground control points. If you open this file in Cloud Compare or AutoCAD or BricsCAD or any software that allows you to visualize these points, you will see that the facade that we are going to be working on, it's not a vertical facade, but the facade is actually flattened out. So that's very easy for the digital elevation modeling and for orthophotographing, because we will actually just put the entire facade in the XY plane rather than having a random XY orientation and having our Z direction going upward. So in this case, the result of our model is a facade where the Y-axis is pointing upwards, the X-axis is pointing on the right direction, and our Z-axis is pointing towards us. And that's a very common practice to work with facade modeling. Very interesting about this is that actually your Y can be used, or your Y-axis can be used to define your leveling of the facade itself. So for example, if you want to have the elevation or all the elevations related to the front door, to the lower part of your front door, for example, you can just set that to a value of 100 or 10 or even 0. And from there you can calculate upwards as a function of your Y-axis. So that's very convenient. I downloaded these images and I put them in a appropriate folder. So that's what you see here. I have a logic name, pg_05_demo_data. And I have all my data here together. And what I can do then is just go to Agisoft. So I will actually skip all these slides because you know how to do that. And I will go to this slide. So actually where I will continue is just slide 30. My idea now is that you will not follow the different steps that I will be doing, but I will just show you how to generate a model using ground control points. So, there's a chat. Allez. Let me see how I can access. Hi. Hello to you too. I will add my photos. I will add all the photos, including my GCP overview, which is obviously not used in my georeferencing. So here you see all the different pictures that are used for the data acquisition. And here is our GCP overview. So I can click on it and I see here the locations of the different ground control points. I will select all the photos except for my GCP overview and I will calculate my image quality, estimate image quality. Should normally go very fast. Voila, there they are. And apparently the photos are in very high quality. And what I will also do, I've loaded this photo in my project. I will not use it for my image alignment. So I right click on it and I say disable cameras. Now you have this red icon assigned to that coordinate. If I look in my workspace and I go here to reference, you will see that there are already coordinates assigned to each and every photo. And that's always also the reason why you see some points here. So if you have taken your photos with a drone, under normal circumstances, there is a GPS coordinate assigned to each and every photo, meaning that Agisoft can already start with working with these kinds of coordinates. Of course, the GPS sensor of your drone has an error of approximately 3 to 5 meters if you're working with a normal drone. So I'm not considering an RTK drone in this case, but a normal drone 3 to 5 meters, which is absolutely not sufficient for facade modeling. And that's why I also used the locally defined coordinates. So what I do here in my reference pane is I select all my photos, I click here, and what I'm actually doing here is during the data processing, I will just disable all my coordinates, all the coordinates that are assigned. So from the beginning on, I will already work in a local coordinate reference system rather than working in WGS84 in this case. If you click here under settings, you see here reference coordinate reference system WGS84. This is obviously set to local coordinates. By the way, if you're working for an airborne campaign, or if you have measured using a total station or GPS in an absolute coordinate system, you can select your national coordinate system or UTM-84, UTM 31 North or 37 North. If you're working in, I think this was for 35 North was in Greece, it's Athens, I think. And like as you have seen in GIS, you can use the EPSG code to find your own coordinate reference system. But in this case, obviously, we will work in a local system, so I will just press OK here. I align my photos, generic pre-selection, should go quite fast. Good moment to see if there are any questions in the chat. No, it's empty. So here I have my photos and my the sparse point cloud of my facade. What I also see is that here under aligned, all the photos that are included in my project, they have this little V sign, except of course for the GCP overview that doesn't have a V sign because I disabled it. So far I am successful. The next thing I have to do is import my ground control points. I will also do that here in my reference window. So I will go to import in reference. I will click GCP or the GCP file, the ASCII file where I've loaded my photos. Here my file is imported as a CSV. So I'm importing a CSV file, comma separated file. It has local coordinates. Also here you can select another coordinate system if you have measured your coordinates in another coordinate system. Very important is the delimiter. So by default, for example, a comma separated file is separated by commas. And if I say, okay, my delimiter is a comma, so the delimiter is this the character that will distinct one column from another column. So if I go back to my original file, I press it here, I open it here, you will see that my delimiter is a tab. So I have my ID tab, my X tab, my Y tab, and my Z tab. And the decimal sign here in this case is a point. Definitely not a comma, but a point. So I have to say, okay, my delimiter is a tab. And then the next thing I have to make sure is that my label is indeed the ID of my points. Can be in any name, but in this case, I call it hashtag ID. I have my X coordinate assigned to my X column, my Y coordinate assigned to my Y column, and my Z column assigned to, or my Z coordinate assigned to my Z column. If, for example, my X and my Y axis are changed, so if you're working, for example, in Japan, they're used to do that. The X and the Y axis are converted there. Then you can change those column values here by just saying, okay, this is column 3 and this is column 2. So by doing that, you're actually just rotating your axis. Obviously, that's not the case here. So I can say 1, 2, 3, 4 is label X, Y, Z respectively. I don't have additional fields, so the accuracy label that is assigned to my Cartesian coordinates, I will keep it disabled. I have no rotation values. That's most of the time that's the case when you're working in with kinematic, with mobile mapping, or with airborne, conventional airborne photography. There's a rotation value assigned to your photos. And also, obviously, I don't have an accuracy for my rotation values. So this is set. I have my labels X, Y, Z. I can press OK. And then it will say can't find match for GCP 1. It is possible to start your project by assigning ground control points without coordinates to your different photos. And if the name of the manually assigned coordinates correspond with the name, with the labels of the file that you're importing, then it will automatically assign the correct coordinates to the manually assigned reference points. I normally don't do that, so I start from scratch. And after working from scratch, I'm just importing my, my CSV file. And then, of course, there are no ground control points available, so I will have to assign to create new markers for each and every point. So obviously this is yes, this is yes. I know that all the 9 points are not available yet, so I just press yes to all. And the result of that, let me enlarge this screen a little bit. Voila. The result of that is that under my cameras, for which I have disabled the coordinates, I also see the list of my 9 ground control points with the X coordinate, the Y coordinate, Z coordinate, expressed in meters. So make sure that you don't see any non-metric coordinates over here. I have an accuracy field. This accuracy field is used as some kind of a weight for the triangulation. It's by default, it's 5 millimeters. We will not discuss that too much. And after assigning our coordinates to the different pictures, you will also see a metric error, so an error expressed in meters, a number of projections, so how many times does a certain ground control point appear on multiple pictures, and an error expressed in pixels. But we will see how that works. So if I go back to my my GCP overview, so let me click it here. I will just start with a point that is very easy to detect. So for example, here I have a metal. I'm quite sure that there's an official architectural name for things like that, but let's call it a metal structure on the left side of this arc. And I will tell you that this is on top of the facade. If I go back here, you will see here GCP tree. So let's start with that one. And in order to do so, I will go to a photo where this GCP tree is apparent. So here, we can even start with the first picture. So 00464. I go to that location by panning and zooming, and then I right click and go to place marker, and I say this is GCP tree. I can do the same for the next picture or the next GCP, so GCP4, for example. That's the metal structure on the other side of the arc. I can verify that by looking at this here. Voila, GCP4 is just on the other side. So let me go there. Also visible on this photo. Right click, place marker, GCP4. Now you see that I have assigned GCP3 and GCP4 to one photo. They both appear in one photo. So here the value changed to 1, from nothing to 1. And since I only have 2 points on 2 photos, it is impossible to calculate an error because I don't have any redundancy yet. The next thing I will select is this other easily distinctible point, point number 5. So let's see where that is situated. Point number 5 is on the right, the inner edge, edge of the cross. Also visible here on this photo. So the right side, right upper part of this cross. Right click, place marker, GCP5. And now, if I press update, not enough reference data. Now I have to do the same on another photo. So I already have, obviously I have to do it on another photo. I assigned 3 points to one photo. I will take another photo and you will see here these dashed lines, these red white dashed lines, these are actually the epipolar lines that I illustrated in the previous presentation. Let me see if they're also here. I don't think so. No. So the lines that you see here are the same lines as the lines that you will see also not here. Just a moment. Yeah. So these lines, this L accent line and the L line, this is actually the epipolar line that you see here, or the epipolar lines that you see here. This also means that, for example, here, you see GCP5 on the right side of my screen. That means that Agisoft is estimating that GCP5 is somewhere on this line. And indeed, we have selected this point because it's easily distinguishable on the upper right side of the cross. You see that it's not exactly coinciding because of modeling errors. GCP5 is actually here. And now the point is gone. And we can go to the other point. I know that GCP3 is over here. So now I will also convert an epipolar line to an exact point. And I have GCP4 situated right here. So now I have 3 points selected on 2 photos. If I go to my model, I also see GCP 5, 4, and 3 in my sparse point cloud. And interesting now, I have 9 ground control points. These 9 ground control points appear on multiple photos. I have, how much was it? 15 photos in total. So it's it can be quite a job to do that manually. The interesting thing is that I already have all my photos aligned, so relatively I already can make a very good estimate of where my coordinates should be right now, because of the fact that I already assigned multiple points to multiple photos, 3 ground control points assigned to 2 photos. So in this case, if I press update, Agisoft will actually estimate the location of all the other points in my 3D model. And if I go now to a random photo, what you will actually see is that although we have not assigned GCP 4, 5, and 9 to this photo, Agisoft makes quite a good estimate of the location of this photo. And these estimations are visualized by gray flags. So if I go back to the second photo, the green flag are the points that I already assigned. The gray flags are the points where Agisoft has made a very good estimate of it. Go to another random photo and you see here GCP1, GCP7, 8, 3, and 4, and GCP2. The thing that you will have to do now is just go to the points and fine-tune the different coordinates. In this case, for point 7, so point 7, let me show it on the overview. If I look on point 7, it is on the sharp edge, the outer edge of this white stone structure. And in this case, on this photo, it's not very easy to see that point. If there is doubt about the location of a point, it is better to leave it there, to just not to touch it, and to go to another photo where you can easily distinct that point. So for example, here it's a little bit more obvious. Point number 3 was also a very obvious point. Point number 4 is clearly not visible, so don't touch this point. Also don't remove it. All the estimated points are not incorporated in the process. This can be used, point 1, used here, and point 2 can also be used. It's actually also the crossing of this point. And by doing that, you can just go to different photos and assign the different coordinates to certain pixels. You can see that this is quite a time-consuming process. So a very convenient way to speed up this process is to select one of the points here. So let me take GCP1, right-click on it, and then filter photos by mask. That's the first thing you can do. And by doing that, and by having your zoom in a certain level, by going from one photo to another, Agisoft will automatically go to that certain location. So it will actually increase the performance of the selection of your different ground control points. Actually, you don't even have to select them all. The only reason why you have to select them all is that it will make sure that if you select a photo, that the photo of the ground control point is actually apparent there. So now I only have a few photos from the entire population of photos, and I can just select a certain photo, and you see that GCP6 is automatically used for panning and zooming. Take point GCP2. This point here, this point, and this point, and this point. Very interesting in this case, especially for the people that are familiar with statistics, mathematics, and maybe even a little bit of land surveying. If you're aware of these techniques, you will know that in order to calculate errors, you need data redundancy. So it means that if you have, for example, 3 points assigned to 2 photos, it actually means that the error that you will see is definitely not meaningful. So you need data redundancy to say something about the quality of your model. And that's actually what I'm doing here. I only need a few points. I'm making a lot of redundancy here. I'm just over exaggerating the amount of markers that I'm including. And by doing that, it will allow me, the software will allow me to actually calculate a proper error analysis. So let's take, for the last one, point number 8. Make sure that I have everywhere at least, let's say, 4 points available. At least 4, so let's take. This is not very obvious, so I will just unpin it. Remove it, I'm sorry. Voila. Now, point number 1. Modify it a little bit. And point number 7. So let's assume that we are ready here. We have make a very nice population. What you see now is here, for each and every ground control point, we have an error. And the error, the metrical error in this case is 1.4 centimeters, which is definitely not sufficient for a facade like this. And we have an error of 0.66, so let's say 0.7 pixels. So the RMS, the root mean square error, is 0.7 pixels and 1.4 centimeters. Also, we see here in this case that our ground control points are still positioned and oriented in our 3D space. We also see that if I flatten my space, that the Z is indeed pointing towards us. If I have a frontal side of it, our Z is pointing towards the user. My Y-axis is positioned upwards, and my X position is pointing to the right. So what I can actually do now is, after saving my project, which is obviously something that I should have done. After saving my project, I can actually use these ground control points to optimize the the quality of my image alignment. So the image alignment itself and also the correction, the self-calibration of my entire model was solely based on the images. What I'm actually doing now is adding a new constraint to my model, saying that, okay, these pixels should be related to each other, but they are not only related because of the pixels, but also because of the ground control points that I assign to them. So I can click here on update to already improve the quality of the ground control points, the triangulation of the ground control points. But I can also optimize my cameras, my entire scene, selecting my different deformation parameters. And by clicking OK, it will actually recalculate the entire image scene. So all my photos are slightly modified, the orientations are slightly modified. And by doing that, so by recalculating the positions of my photos based of including the ground control points and as an additional constraint, I'm also able to recalculate the true position or the calculated position of my ground control points. And after optimizing, you will see that the error should reduce significantly, reasonably. So for example, in this case, I have an error of 5 millimeters and a pixel error of 0.5 millimeters. Now, what can be used as some kind of a requirement for these errors? Normally, what I say is that the error should be around or at 1.5 pixel at maximum. So this value should not exceed 1 pixel or 1.5 pixels. Sorry, 1.5 pixels. And this error is obviously related on the one hand to the quality of your ground control points. So if you measure this with a total station, or if you measure it with a simple ruler, or if you measure it with measuring tape, that will of course have an influence on the error expressed in meters, but also, and that's maybe even a more important parameter, is the ground sampling distance. So imagine that you're working with airborne photographs with a resolution of 5 centimeters. It is as good as impossible to get sub-centimeter quality of your ground control points, of course. So let's assume that this is okay. We have our errors expressed in meters. We have our pixels that are reasonable. And let's do something else. If I take a random photo and I say, okay, this GCP5, it should not be here. It should be here, for example. What you will see then is that my error will increase significantly. So if for some reason or another you misuse or misselected or misassigned, it's better to say misassigned a ground control point to a photograph, you will see an error in meters and an error in pixels that will definitely increase, significantly increase, especially in terms of pixels. And then the thing is, okay, if you select this photograph and you go to all the photos where this marker is available, then you will see, okay, here it looks okay, here it looks okay, here it looks okay, here it's definitely not okay. So we will have to select that one and correct it just by taking it and assigning the correct location to it. And then you will see that automatically the model will increase. The quality of the model will increase again. The same is also true for mismeasuring the ground control points. So if one of these values are mistaken, so for example, if you take, copy that value and let me make it 19 meters, you will also see that the pixels, of course, the pixel value will not change too much because all these pixel coordinates are still pointing to the same coordinate, but you will see a metric error that is significantly larger than the rest of your coordinates. So this is also an indication, or this is an indication that one of your ground control points were measured incorrectly. And then you can just modify it again, or maybe even disable that point. You can disable points. You can remove points from your process in order to optimize your point cloud. Are you with me so far?
More or less.
Yes.
What I would like to suggest, because I'm almost talking for an hour now, let's have a little break of 10 minutes. Then after the break, I will show you how to make the digital elevation models and how to make a digital elevation model and an orthophoto and how to interpret the quality reports. And then during the break, I will process this project so that we can just continue it. I think after the break, I will need, let's say, 15 to 20 minutes for further explanation. And then I will not do any more, I will not give you any more content, but I would like to keep this meeting open, that you can try at least to assign coordinates to your, to this model. So during the break, I think it's a very good idea also to import the photos, align the photos, so at least that you make sure that you have, let's say that you have something similar as this in your project. And then after finishing my discussion about the orthophotos, the DEMs, and the quality report, you can work on the assignment of the ground control points. And then in this meeting, if there are any problems, I can just try to clarify things if it's needed. Are you okay with that proposal?
Sure.
So, okay.
Yes.
Okay, then let's meet. Right now it's 5 to 5. So let's meet in 5 past 5, 5 past 5, 10 past 5, something like that.
Cool.
Okay.
Okay.
Cornelis, can you hear me?
Hello.
Hello. Do you have a break?
Yeah.
Okay. You can pause recording.
I did.
You did.
Recording. I should have taken this one. Yeah, voila. Okay. Sorry for the inconvenience. Everything that I just said will also be recorded and put in an MP4 that you can find in the Moodle by tomorrow. So I will just work on it tonight to make sure that this is corrected. Yeah. In that case, I'm afraid that you have you seen, where did I stop? You've seen how I made this orthophoto? Can you confirm that? My screen is now shared normally.
Yes, for me it stopped when you were exporting the orthophoto.
Okay.
Yes, me too.
Okay. Then let's go back to so export orthophoto. Yeah, what I did here, export orthophoto. So by the way, I'm very sorry for the inconvenience. So this was the screen I was discussing with you, but that you couldn't see. The resolution of your final orthophoto, normally in the normal circumstances, I try to round it. So 2.5 millimeters, for example. It's just a matter of making it more easier to manipulate it and to have a better background on the image analysis if you want to use it for further data processing. You can select your background color, white or black. I will not touch this one. I also explained if you want to if you end up with an orthophoto with very large dimensions, so in this case it's only 1677 by 2758 pixels, so that's a reasonable amount. But if you end up with orthophotos that are very, very large, so 10,000s and 10,000s of pixels, it might be a very good idea to split your orthophoto in blocks with a reasonable amount. So let's say 1024, for example, by 1024. Again, here also try to make it a power of 2. I will not do that here because my dimensions are reasonable. If I would press it like this, so if I would export my orthophoto with these parameters, I will actually end up with four orthophotos. One of them will be fully colored in 1024 by 1024 pixels, and the other 3 orthophotos will just be portions of this orthophoto. Once again, I will not do that. If you're familiar with image processing, you will find this very convenient. This is the way how the result will be compressed. So compression for TIFF, multiple availables, lossy and lossless compression algorithms behind it. Normally with the LZW, I'm not an expert on data processing, image data compression. But normally, to the extent of my knowledge, LZW doesn't give you any loss of quality, loss of pixels. If you're fine with data losses for the TIF format, you can use JPEG, but I would not do that actually. A percentage for JPEG quality, if you want to export to JPEG, it's also available, and the ability to write a GeoTIFF, including an alpha channel, or the big TIFF is for data, also for processing large data files. So let me go back here and export it again. Voila, I will just overwrite it. And the same parameters also hold for exporting the digital elevation model, again with a resolution. I would preferably round these values as well. It's not mandatory, but you can do that. I will use a logic number for no data values. It will be very easy to use these values in the GIS environment. In this case, also the option to split your final results in blocks. Yeah. https://geo.horigen.be/heritage/sc. So this should normally work. Voila. I just uploaded for your information the link for downloading the photos. Yeah, and here again you can just select your or define your file name, the export format. So export format for the orthophoto was TIFF, JPEG, GP2, PNG, and bitmap. And for the digital elevation model, so the raster, where we'll assign a floating value to each and every pixel, so an RGB value as with a photo or an orthophoto. But in this case, we can work with TIFF, with ASCII, BIL, or just another ASCII-based XYZ formats. But normally you would work with a TIFF. And I will also replace that one. Then just before you correctly mentioned that I was not sharing my screen, I was explaining about export the processing report. So I will give it a title again. So Facade Ghent, Belgium, with my name and the date of today. I will export, this is just for illustration, the top XY plane, which is also coincidentally the plane of my orthophoto projection. And then here in this case, I will say 05 QR quality report, or PR, processing reports, just to make sure that it's very easy to find this, this model. So let's open it. It's already opening automatically. I already briefly explained to you how to read and how to work with this report in the previous session. In this case, we have some more information, which is very convenient if you want to use these data and when you want to incorporate your 3D models in project reports. So the classical archaeological excavation reports or project reports in general. So again, you get an orthophoto of your object or an illustration of your object, a coverage of the object in terms of photos. And here we have some additional information, which is quite interesting. The number of images, which is 16. It includes my GCP overview. And that's why our camera stations is only 15. So we used, from these 16 photos, we only used 15 photos. So the GCP image was excluded. So that's actually, if we go back here to Agisoft, it's actually, let me go back to all cameras. It's actually this photo that is not incorporated in our model. And that's the reason why these values are not the same. The flying altitude is in this case the distance from the drone flying in a vertical fashion to the facade itself, an average flying altitude. The ground resolution 2.35 millimeters per pixel. This is our ground sampling distance. Ground sampling distance can also be calculated using the equations that I showed you last week. The coverage, the area, the size of our object, the number of tie points, the number of projections, so the time points, the matching points, and the total number of characteristic points. And the reprojection error is actually the error that you will see. Not here, but this is a measure for calculating the total error of your matching points, which should also be lower than 1 pixel. Information about the camera model. It's not pre-calibrated. The lens distortion parameters. The quality of our ground control points. This is also a page that was missing before using the ground control points, or the discussion of the ground control points. Apparently, it all looks reasonably fine. GCP1, which was also a very difficult point to distinct. As quite a large error of 4 millimeters, also GCP7 minus 5 millimeters. So this is just an illustration of error ellipses, but if you want to get a better overview of it, you will see here a table of all the individual points with an error in X, Y, and Z, a total error. So this is just a 3D error. Pythagoras applied on these values will give you the total error, and the error expressed in pixels. The value behind the brackets is the number of projections, so the number of projections for each and every point. And then the average error, or the mean square error for X, Y, Z, and the 3D error in pixels and in meters, in millimeters in this case, are presented in the last line of this table. Very important, or at least I always mention that to my students that follow land surveying here in Ghent. It is always a very bad idea just to copy paste this table, especially for the surveyors or the engineers or architects amongst you. You will not understand why, most probably, because these values are given in millimeters, and it doesn't make sense to give values in like this 8 here, for example. The meaning of it, it's like 80 nanometers, nanometers in this case. So if you want to use these values, please make sure that you round it and that you make logic values of it. The number of significant values should be correct. An overview of the digital elevation model, again, with the number of, the resolution of your point, the resolution of the DEM itself, and the number of points per square centimeter in this case. So just a point density projected on that digital elevation model. And then last but not least, the overview of all the processing parameters that I implemented. So if I want to modify something, I can just go back to this report and fine tune my, my model. Voilà, that's for the quality reports. And once again, very useful to keep track of. So let me go back, make sure that I covered everything. So that's the last thing I want to show you. Before going back to the presentation, let's see what's happening if I open QGIS. Let's see what happens if I import my, my orthophoto and DEM. Voila, here's my QGIS environment, and let me just open it. Of course, I'm not working in an absolute coordinate reference system. So while importing my data, it will automatically go to WGS84. And that assumes, and that's very important to mention here, that assumes that if I measure a distance using QGIS, that the distance from here to here is actually a distance calculated in meters, but derived from degrees. So it actually means that we are going around the globe a couple of times. So this definitely doesn't make sense. We should better take a metric coordinate reference system to start with. So let me take these out. Take a Belgium coordinate system or any planimetric coordinate system, and then import the data again, and definitely not use WGS84 in that case. If I do the same now, I can get a value that is more reasonable. I have here the 3.3 meters. And also I can, if I measure the entire surface of my orthophoto, ja, zo lekker. No, not an angle. I want to measure an area. So if I measure the area, I get an area of, let's say, 28.9 square meters. And if I go back to my quality report, what I see here, yeah, it's most probably because I set some pixels, but I also have a coverage of 28.7 meters. But this all looks fine. And for your information, just for your information, if you want to make some nice illustrations of it, just double click on the digital elevation model, set this on hillshade. Voila, so now I have the hillshade representation, and I can change my transparency, and then you get something like this. So like something like a pseudo 3D visualization. And then in QGIS, you can do further editings on these on this orthophoto. The last thing I would like to discuss with you, before doing that, just 5 seconds. Anna, kan je alsjeblieft die schoenen niet aantrekken? Ik ben die les aan het geven, meisje. Okay. The last thing I would like to discuss with you is the case when you don't have any ground control points available. So, or if you have your ground control points available, but you don't have a total, they are not acquired with a total station or a laser scanner or anything like that, is that you can also use something like rulers or just reference measurements. So, for example, a couple of years ago, I was in Honduras, and there in Honduras, unfortunately we didn't have a total station with us. But then they asked us to make a 3D model of lithics or pottery. No, this was in Greece. This is Greek pottery. This was in Honduras. And what we actually did, we used this this paper with millimeter distances between parallel lines, and we just draw with a pen. We draw our targets on that paper, and by using that and positioning our artifact in the middle of that paper, we can actually just assign the coordinates of that of these coordinates to the different images that we have taken. So you just arbitrarily say, okay, if this is coordinate 0, 0, 0, so 0 x 0 y 0 z, then this is 10 for x, 0 for y, and 0 for z, and this is 10, 10, 10, 10, 10, 0, and this is 0 for x, 10 for y, and 0 for z. And by doing that, you're actually making your own coordinate reference system. Another thing you can do is take these perpendicular ruler systems, or just a ruler in general, where you can just assign the coordinates to a line, for example. So if you say, okay, this is my y-axis, this is my x-axis, and you can just manually assign your coordinates to the lines of the ruler. A last thing you can do, and I would like to mention here, I'm not going to demonstrate it, but just show you by the presentations themselves, is the creation of reference bars. Or actually, I can demonstrate it. So what you can do in this case is say, okay, I have a point here, for example. Let's say this is point number 1, this is point number 2. And instead of assigning coordinates to them, so instead of saying, okay, this is coordinate 0, 0, 0, and this is coordinate 10, 0, 0, for example, you can also say, okay, I assign my points here, 1, 2, 3, 4, and I say that the distance from point 1 to point 2 is 10 centimeters, the distance from here to here is 10 centimeters, from here to here is 10 centimeters, etc., etc. And in that case, you can actually also make your own reference system. Very interesting example in that case. If you know Pythagoras, you know that if let me write it down. Let me take a piece of paper and explain it to you. 2, 3, dit is 4. Dit is 4. No, I missed it a little bit. This is 4. 9 is niet. Yeah. 3, 4, and 5. I'm sorry, because this was not planned. So of course, if you are familiar with Pythagoras and you make a triangle, so a physical triangle with a size of 3, a size of 4, then the sloped area has a size of 5. So you can make any multiplications of these values, and by making a physical frame of these values and using them on site, you can actually have a very mobile way of working with a coordinate reference system. There's a question probably about it. Thank you. Okay, you're welcome. So you can actually make your own coordinate reference system and make it physical and use it on site by just going to a construction site and ask for a piece of wood of 3, 4, 5, 5 meters, for example. So if you want to do that here in Agisoft Metashape, and we know, for example, that based on a measurement that we've done, of course, on site, let's do it in QGIS in this case. I will just measure the distance from, let's say, from here to here. And this distance apparently, no, it's not an area, it's a distance from here to here. This is a distance of 1 meter and 7.7 centimeters. So that's what I wrote down in this case. And what I can do now here in my photo, for example, is say, okay, I have a point, another ground control point here. And I can go here and say, okay, add a new marker. These markers obviously don't have coordinates. They have a coordinate now because these are estimated coordinates, but I didn't assign them to them. But when I select my point 1 and point 2 that I just manually assigned to them, to the object, right click, create scale bar, and then here you will have a distance, a scale bar, where I can say, okay, this the distance from point 1 to point 2 is equal to 1 meter and 0.77 meters. And in that case, I get, in this case, an error of 1 centimeter, 1.1 centimeter. So currently, in the current model, it is an underestimation of my distance. But this is just, normally I would not implement it in a model where I already have my ground control points measured by total station. But if you don't have a total station, but you have a ruler, you can just use these kinds of measurements to at least to scale the dimensions of your model. And that's also what is expressed here in this slide. So you place your marker without ground control point or without coordinates. You select your point, so select 1, control, select 2, control, and then you right click, create marker, and you can assign a certain distance to that point. Voila, I think that is that. So you have your ground control points. I don't know, do you have any questions so far? So actually what I did today was discussing with you session 5, so topographic workflow for georeference model. So it's actually a repetition of what we did during for the first time when we worked with Agisoft, but in this case we're working with ground control points. Normally you learned how to use these ground control points in Agisoft and how to generate digital elevation models and orthophotos from these data. And also I gave you a sneak preview on image-based models, the use of image-based 3D models in GIS like QGIS or ArcMap or any other GIS software. We will not cover that in the rest of the specialist course. So this is just for your own information. Also the task is something that you can do for your own information. But if you don't have any more questions, I would invite you to work on the task. So in the tasks you will find, in the Moodle platform, you will find 2 tasks. The first one covers an archaeological excavation in Romania, accompanied with ground control points. So let me show you these data. It's task 1. It's a series of airborne photos of an excavation. And by the way, I would like to ask you to deal these data confidentially. The location of the ground control point. So this is easier than working with the facade, because you see here the black and white targets that are available left and right. The location of the ground control points, you can normally find it where? No, I will publish that. So if you have doubts about the location of the ground control points, I will make sure that you get an illustration of the location of the ground control points. And in this case, generating a point of the georeferenced point, georeferenced model of your own 3D model. Normally, you already generated a locally oriented 3D model of your artifact, and I would like to ask you to go back there, do some reference measurements, and then try to implement this slide. This slide on the model that you obtained. So, for example, if you made a model of the facade of a church, for example, try to make a measurement on one of the doors or the windows or something like that, and try to orient and at least scale your model so that you are able to do some reference measurements on it. Voila, I will stop sharing my screen from here. And I don't know if you have any questions for now that can be